So we'll apply the steps. Once the simplex table is established, so as you know, the linear programming problem, we have n number of variables and m number of constants and one objective function. This objective function in the simplex table, that is the last row of the simplex table, represent the objective function, the last row of the simplex table. That is crucial. And there are, so the top one is the label only. So this table, whatever we are presenting, this is called the condensed form of the simplex table. There are two tables. One is the extended table, another is the condensed tables. I am presenting the condensed form of the simplex table. Okay, so why it is condensed? So when we will discuss about the numerical example, there I will state. So the last row represents the coefficient of the objective function. The D represents the value of the objective function. And here in this table, we have variables like basic variable and non-basic variables. Z1, Z2, Z3, then ZU, finally ZM. These are the value of the basic variables. Z1 with respect to first row, Z2 with respect to second row, ZU with respect to the uth row, and Zm with respect to the last row, with respect to the mth constant. These are the basic variables. For a constant, we include a basic variables. There are n number of non-basic variables like x1, x2 up to xn. Non-basic variable, and these are z1, z2 up to zm. These are the basic variables. We are giving different name, basic variable, non-basic variables. If you put same name like x1, x2 up to xn, then xn plus 1, xn plus 2 up to xn plus m, there will be some confusion. So in the very beginning, I am giving different name. Basic variables like z1, z2, zm, they are the basic variable. Rest are the non-basic variable, and z is the value of the objective function. Okay, this table. So in this table, so generally I have already mentioned. So we solve a linear programming problem using the basic feasible solution method. If you are assuming there are in the system X equal to B, there are so n plus m number of variables out of n plus m. So m numbers are basic variable, rest are the non-basic variable. We set all the non-basic variables to 0, like x1, x2, xn, they are 0. So then we'll find the basic variables, like basic variables are z1, z2 up to zm. So once you are setting the non-basic variable x1, x2, xn 0, the basic variable value becoming z1 equal to b1, z2 equal to b2, and so on, say zm equal to bm, and the value of the objective function z is becoming small d. So in the very first table, that is the initial simplex table. Okay, next. So these are the steps. So step 1 say select the most negative element in the last row of the simplex table. There are altogether m plus 1 number of rows. So consider the last row. In the last row, select the most negative element in the last row of the simplex table other than the d value. So d is representing the value of the objective function. Okay. So apart from that, another n elements are there. So you will select the most negative element. All have joined? Hello? Hello?
Yes.
Yes, sir.
And you are able to see and be able to hear? There is no problem. So in case if you find any difficulty, please inform me, because I am looking at the slides, not looking at your face. Okay, so the step 1. So if you find there is no negative element, we conclude that the present table is optimal. If there is no negative element in the last row of the simplex table, then we conclude that this is the optimal table. We stop the method. So if there is a negative element, we proceed to step 2. What is step 2? Suppose in step 1, we find the element minus CV at the column, at the bottom of the bth column, at the bottom of the bth column, that is the element most negative, that is minus CV. Then what we should do? Form all positive ratios of the element in the last column to the corresponding element in the bth column. So because the minus CV, it is representing the last row element in the bth column. So we will form ratio in this manner, that is BI divided by AIV, where AIV is positive. If AIV is 0, we cannot divide. If AIV is negative, we cannot divide. Only we will have positive ratio in the form, that is BI divided by AIV. The element, say AUB, which produces the smallest ratio, that is BI divided by AUB, is called the pivotal element or the key element. That is crucial. So whichever the minimum ratio, minimum positive ratio, so with respect to AUB, it's called the key element or the pivotal element. That is the step 2. If the element in the bth column, elements in the bth column are negative or 0, in case you find the elements are in the bth column either negative or 0, the problem is called unbounded. So there we will stop. So see, when you will stop, if you find there is no negative element in the last row of the simplex table, then we stop. And if you cannot proceed, because with respect to the bth column, all the elements are negative or 0, the problem is unbounded, we declare, then we stop. If not, we move to step 3. What is the step 3? So step 3, there are several sub-steps like A, B, C, D, E. So what we should do? So we'll discuss one by one. In step 3A, interchange the role of XB. XB stands for a non-basic variable, and ZU stands for a basic variable. Interchange the role of the present basic variable and non-basic variable. That is, relabel the row and column of the key element while keeping others label unchanged. Don't change any other label, only basic variable and non-basic variable in that table. So we will only interchange. I will mention which one we should interchange in the example. So then once it is completed, say, see, from one table, when we are going for another table, we will draw a similar table. After drawing a similar table, then interchange the role of XB and ZU, these two level. Other level remain as it is. Then we will try to fill up this table. Replace the key element or the pivotal element. We are naming as UB, the key element. UB is equal to our P. pivotal element or key element by its reciprocal, that is 1 by P. So then if it is 1 by P, that reciprocal is becoming 1 over UV, AUV. That is the key element. We are taking the reciprocal. Similarly, with respect to the key element, there is a particular row and there is a particular column. So with respect to the row element, replace the other elements other than the key element of the row of the pivotal element by row element divided by the pivotal element. Okay. Then we are moving to step D, 3D, replace other elements of the column of the pivotal element by negative of the column element divided by the pivotal element. Finally, so other than the pivotal element, other than the row element and the column element, there are several other elements. So that we will compute in this manner. P is our pivotal element. Let us form a rectangle. So in the 4 corner, there are 4 elements. P is our pivotal element. With respect to the P, in the opposite corner, there is an element called S. Other 2 elements you can name as Q and R. If you are calculating the value of S, in the next table, it will be S dash or S star. This S star will be P into S minus Q into R divided by P. P is positive, not 0, not negative, it is only positive. PS minus QR divided by P. So using this rule, you complete all the elements in the new table. So after that, so once it is completed, we move to step 1. What do we do in the step 1? We check whether there is any negative element in the last row of the simplex table. If it is yes, we compute using the similar rule. If it is no, we stop, saying that this is the optimal solution. Okay, so it's very simple, but when you calculate, you have to follow the rule. So there are several tables. In several books, you will find different table. I will discuss all the tables. So one of the table is known as condensed table, and other table is known as extended table, condensed and extended. Okay, so generally, if you are solving a problem using pen and paper, the condensed table is fine because we have to compute less number of elements. For the extended table, you have to compute little more. So we will try to use only condensed table, not the extended table. However, I will tell you all the tables, how we will compute using the extended table, how we will compute using the condensed table. Okay, this is fine. Hello? Now, sir, let me move to the numerical example. Can you see this example? Hello? Are you able to hear?
Yes, sir. Yes, sir. Yes, sir.
So yes, my question is, so since you are, this is the first table, try to draw a table. So, and you name it accordingly. So, see, there is no option for here. I have made slides and I have made several problem also. I will show you, but you try to draw at least one table so that it will give you some confidence what exactly we are doing. Okay, this is the problem. The problem is we like to maximize z equal to x1 plus 3x2. Generally there is a d. plus D. Here D is not there, so D equal to 0. Maximize Z equal to x1 plus 3x2 plus D. D is not there, D equal to 0. Or if you like, you can put something like, let us say D equal to 10, no problem. Okay. So here D is not there, D equal to 0. Subject to x1 plus x2 less than equal to 100. x1 plus 2x2 less than equal to 110. Then x1 plus 4x2 less than equal to 160. You can see the right hand side element, the resource level are 100, 110, 160. And our x1, x2, the actual variables, what we are interested to find out, they are non-negative. Non-negative. If nothing is mentioned, x1, x2 are not mentioned, nothing. So you can say these are the three variables. 3 means that can be positive, that can be negative, that can be. So in the definition it is given, these x1, x2 are, in the formulation is given, they are non-negative. Nothing is mentioned means they can be negative also, but here they are non-negative. Now we like to add slack variables. Why slack variables? The reason is, for this constant can be either less than equal type, can be greater than equal type, can be equally type. So we have to introduce slack, surplus, artificial variable according to the need. So here there is a need of using slack variables. All the three constants are less than equal type. First one is less than equal type, second one is less than equal type, third one is less than equal type. So you will introduce slack variables like Z1, Z2, Z3 respectively to these three constants. Okay. So since they are slack variables, these Z1, Z2, Z3 are non-negative. So we are writing in this form x1 plus x2 plus Z1 equal to 100. Z1 is non-negative. Okay. Or this you can express as minus x1 minus x2 plus 100 equal to Z1. Why you are expressing in this manner? The reason is the Z1 depends on x1 and x2. Z1 depends on x1 and x2. Once I am setting x1, x2 0, the Z1 value is becoming 100. Similarly, x1 plus 2x2 plus Z2 equal to 110. You can write minus x1 minus 2x2 plus 110 equal to Z2. This Z2 depends on x1 and x2. So once you are setting x1, x2 0, then Z2 is becoming 110. Similarly, x1 plus 4x2 plus Z3 equal to 160. This is simply saying minus x1 minus 4x2 plus 160 equal to Z3. From these three equations, what you observe? Z1, Z2, Z3, these are Z1, Z2, Z3, these are the basic variables. And x1, x2 are the non-basic variables presently. These basic variables are the function of non-basic variables, linear function of the non-basic variable. Z1, Z2, Z3, Z1 is a function of x1 and x2, Z2 is a function of x1 and x2, Z3 is a function of x1 and x2. Okay, these Z1, Z2, Z3 are the basic variable and rest are the non-basic variable. Okay, this. Now, this system we want to put in a tabular form. So, this is my table. Okay, please make a similar table. Please make a similar table. I'm waiting for you. Okay, this table, as you know, there are 4 rows and 3 columns. There are 4 rows and 3 columns. So you make a similar table. If you have pen and paper, please make similar table. Okay, so this table we can name as initial simplex table. Okay, initial simplex table. See, with respect to 4 rows, first row representing the first constant, second row representing second constant, third row representing third constant, and the last row representing the objective function. The objective function. Okay, so there are some label you can see here in the first column at the above. There is an index something like minus x1. In second column, minus x2. In third column, there is 1. Okay, first column minus x1, second column minus x2, third column 1, and you can say row wise. You can see here I have written here 1, 1, 100, then equal to Z1. The meaning is like this. So Z1 equal to minus x1 minus x2 plus 100. 100 into 1 equal to 100. Okay, so minus x1 minus x2 plus 100 equal to Z1. See, this we are writing in this form: minus x1 minus x2 plus 100 equal to Z1. Similarly, second row, minus x1 minus 2x2 plus 110 equal to Z2. Then third row, minus x1 minus 4x2 plus 160 equal to Z3. Finally, there is objective function. The objective function equal to Z or Z equal to x1 plus 3x2. D is not there, D equal to 0. So we can write in this form: minus 1 into minus x1. The product equal to x1. Minus 3 into minus x2. This product equal to 3x2. So x1 plus 3x2 plus 0 equal to Z. It is clear? Have you completed this table?
Yes.
Have you completed this table? Tell me please yes or no.
Yes, sir.
Okay. Now, so here itself, this table you can name as initial simplex table. You can put table 0, T0, no problem. Okay. Or you can write initial simplex table. This is representing our problem. This is representing our problem. So from this, there is some summary. So there are 2 categories of variables: basic variable, non-basic variables. Okay. So see, we have here how many columns? First column with respect to x1, second column with respect to x2, the third column is the constant right hand side value 100, 110, 160. Only 2 columns. These 2 columns are third column, of course, the value of B1, B2, B3. These first 2 columns. So on the top, there are non-basic variable like x1 and x2. There is no space for the basic variable in the column. However, in the row, there is basic variables Z1, Z2, Z3. Z1, Z2, Z3. If you find in a table x1 column is there, x1 column is there, x2 column is there, z1 column is there, z2 column is there, z3 column is there, you will find 2 plus 3, 5 plus 1, 6 columns. That table we can name as extended simplex table. And this table, since the basic variables are not there, we will name this table as condensed simplex table, reduced. We have, so see, if you are including another 3 columns, see, you can imagine how many elements there will be extra. So here there will be, this is a table, 4 rows and 3 columns. The new table, the extended table will be, so another 3 row, so 6 column and 4 rows. So you can see how many elements here you are dealing with. 4 into 3, 12 elements. There 6 into, that is 3 plus 2, 5 plus 1, 6. 6 into 4, 24 elements. So the table, the number of computation here, it is 12, there will be 24. Okay. So you have to do some extra computation. So we are trying to avoid such computation. That is the reason I am using a condensed table, not the extended table. In some cases, we will also use the extended table, and there you will realize what is the difference. Okay. So this is the first table. You can now draw a similar table. Keep all the elements empty. Keep all the elements empty. Here, before that, I'm saying just analyze the last row of the simplex table. There are 2 elements other than 0. 0 says the value of the objective function. Presently it is 0. Why? Why it is 0? Because there are basic variable, non-basic variable. Generally, non-basic variables are 0. Basic variables, it is value is given. Z1 equal to 100. Once you set x1, x2 0, Z1 is becoming 100. Then Z2 is becoming 110. Z3 is becoming 160. And Z is the objective function, that is equal to 0. Okay. So here in every table you will find the value of the basic variable and value of the non-basic variable instantly from the table. So now we will analyze the table whether we can go for the next table or not. The answer is yes. Why? Because there are 2 elements in the last row of the simplex table, -1 and -3. Most negative you are selecting. Most negative is -3. Most negative is -3. Now, so with respect to -3, we have detected this -3 is available in the second column. -3 is available in the second column. Now we'll have positive ratio in this manner. 100 divided by 1. The ratio is 100. 110 divided by 2, 55. 160 divided by 4, that is 40. How will take positive ratio? See, elements in the last column, that is constant. There is 1 is there. Then we have 100, 110, 160. The element of B1, B2, B3. And what is there in the second column? The elements. All the 3 elements presently, 1, 2, 4, all are positive. Neither 0 nor negative, they are positive. In case you find instead of 1, it is -1. Instead of 2, it is -2. Instead of 4, it is -4. We conclude that the problem is unbounded. Here, we are not concluding anything because all 3 are positive. So we have got ratio 100 with respect to first element, that is 100 by 1, 100, 110 by 2, 55, 160 by 4, that is 40. Minimum ratio equal to 40. So this 40 we are getting with respect to this element 4. There is a star mark. First star we have selected because with respect to the most negative element I have put, there is a star mark. So -3 is selected. After selecting -3, we are taking the positive ratio. From the positive ratio, we have, so 40 is minimum. So this 40 we are finding with respect to 4. Then what will happen? This, with respect to 4 and with respect to -3 in the second column. -3 in the second column. And this 4 with respect to third row. There is a label. What is the label? So in the second column, the label is -x2. In the third row, the label is Z3. So we'll interchange. In the next table, we will interchange. Why will interchange? This x2, which is a non-basic variable, it will be a basic variable, and z3, which is a basic variable, it will be a non-basic variable in the next table. So now you draw the next table. You have drawn? You have drawn the next table? Hello?
Yes, sir.
Now, in case you have drawn, now re-level. So level in this manner. In place of minus x2, put it minus z3. In place of minus x2, put it minus z3. In place of z3, put it x2. So if it is given in there minus x2, it is becoming minus z3. And in place of z3, it is becoming x2. And all the other levels remain unchanged. All the other levels remain unchanged. Please complete. So re-level the basic variable and non-basic variable position. Minus x2 is becoming minus z3 and z3 is becoming x2. Other levels remain as it is, no change. Only basic variable, one non-basic variable. This x2, whatever is coming, that is called an entering variable. This z3, whatever is going, that is called a departing variable. The x2 presently is becoming the entering variable. Z3 presently is becoming the departing variable. Departing variable and entering variables. Okay, that's all. Now, after re-leveling, we will try to fill up the simplex table. Try to fill up the simplex table. Okay, so you have completed the table. You have completed. Now I will tell you how to fill up. So in the next table, so there is 4. With respect to 4, there is a particular row. The row elements are 1, 4, 160. With respect to that 4, there is a column. The column elements are 1, 2, minus 3. So column elements are 1, 2, minus 3. Row elements are 1, 4. You leave 4, 1 and 160. Now we like to fill up. Other than the row and the column elements, there are other elements that also we will take care. Okay. So in the next table, the 4 is becoming the reciprocal. So the 4 is becoming 1 by 4. Please write down. 4 is becoming 1 by 4. Hello? Are you writing?
Yes,
this
sir.
4 is becoming
Yes, sir.
1 by 4. You can see here. I will just. This presently, this 4, can you see? This is becoming 1 by 4. Is it all right? Hello?
Yes, sir.
Okay. In the same row of this element 4, other elements you divide by 4. So in this third row, there is a 1. The 1 is becoming 1 by 4. Make it 1 by 4. So in the 1 position, in the next table, this is becoming 1 by 4. For the 4 already you have done once. We will not repeat again. So the 4 was, this 4 is becoming 1 by 4. That I have done. This 1 is becoming 1 by 4 because you are dividing by 4. This 160 you are dividing by 4. This is becoming 40. Complete. So in the same row, this value is coming 1 by 4, 1 by 4, 40. Now, with respect to row work is over. Now I am coming to the column work. Same column. So this there is a 1. In the second column there is 1, then 2, So in the 1 is there in first row, 2 is there in second row, and 3 minus 3 there in the last row. These 4 already have done, so no need of changing again. So this one you divide by 4 with a minus sign. For the column element, you will divide by 4 with a minus sign. So this will be minus 1 by 4. Then there is 2. This 2 is becoming minus 2 by 4. You are dividing by 4 with a minus sign. 2 by 4 is same as half. You can write also minus half. This 4 already have made 1 by 4. There is no change. Then in place of 3 minus 3, this is you are dividing by 4 minus sign. This is plus 3 by 4. Plus 3 by 4. Now we have filled. So these 3 elements in the third row, then 4 elements in the second column. There are other elements. So for that other elements, we have to use PQRS method. What is the PQRS method? So presently the 4 is our pivotal element. Okay. Now I'm talking about this corner element. You can see here. Make it a little bigger font. Okay. So this one, if I'm saying 4 is our P and the 1, in one corner you can see their first row, first column elements, that is 1. So that is our S. So for this position, first row, first column elements, for this position, we like to find the new value. What is the value? The value will be like this: 4 into 1, P into S. So presently S value equal to 1, P value equal to 4, and we have here QR 1 1. So 4 into 1, that is 4, minus 1, 1 into 1 1, 4 minus 1 3, 3 by 4. So this is becoming 3 by 4. You all right? So this is becoming 3 by 4. Okay. Now second row, first column, that element we want to compute. So 4 into 1 minus 1 into 2, that is 4 minus 2, that is becoming 2 by 4. See, first you have computed 3 by 4, then it is 2 by 4. Okay, 2 by 4. The next element already you have computed 1 by 4. Now fourth row, first column element we want to compute. Fourth row, first column elements. 4 into minus 1, minus 4, minus 1 into minus 3, minus minus plus. So minus 4 plus 3, that is minus 1. So this is becoming minus 1 by 4. This is completed. Okay. Now we like to compute in the last column elements in the position. What is that? In the position 100, 110, then 0. Okay. So see here, 4 into 100, you are making P into S minus Q into R by P. 4 into 100, 400, minus 160, 240, 240 divided by 4, that is becoming 60. So it is 60. So second row, third column elements, 4 into 110, 440, minus 2 into 160, 320. So ultimately we have 120 divided by 4, that is becoming 30. So it is 30. Then this element, third row, third column, already you have computed, no need of. Now we like to compute the value in the position 0. Presently Z value is 0. Now we like to improve it. How will improve? So 0 into 4, 0. Minus 3 minus, that is minus 3 into 160. So 480 minus plus divided by 4, that is 120. So it is becoming 120. You all right now? You got this table? Please verify. You got this table? Presently, the value, if I'm talking the row wise, so row wise in first row 3 by 4 minus 1 by 4, 60. Then 2 by 4 minus 2 by 4, 30. 1 by 4, 1 by 4, 40. Minus 1 by 4, 3 by 4, 120. Now, we have put some label. Basic variable, non-basic variable. Presently, the basic variables are Z1, Z2, X2. Basic variables are Z1, Z2, X2. Non-basic variables are X1 and Z3. The value of the non-basic variable X1 equal to 0, Z3 also equal to 0. The value of the basic variable Z1 equal to 60, Z2 equal to 30, X2 equal to 40. With respect to this, earlier the value of Z was 0. Now the value of Z equal to 120. So we have improved or not? Earlier it was 0. Now it is 120. We have improved. How much we have improved? We have improved 120 unit. Now the question is there any possibility to improve further? The answer is yes. Why? Now we check the last row of the simplex table other than the value of the objective function. So Z equal to 120. This you are not checking. We are checking other two elements, that is minus 1 by 4 and 3 by 4. Minus 1 by 4 and 3 by 4. Is there any negative element? Yes, there is a negative element. With respect to this negative element, now you find the positive ratio. How to find positive ratio? In this manner. Positive ratio 60 divided by 3 by 4. How much it is? 60 divided by 3 by 4. How much?
80.
80. Then 30 divided by 2 by 4.
60.
How much? 60. Earlier it was 80. Then it is 60. Then 40 divided by 1 by 4.
60.
160. Okay, 160. Now we are looking for minimum ratio, minimum positive ratio. So where we find the minimum positive ratio? There is a star mark you can see here, 2 by 4. 2 by 4 means it is half. So there is a positive ratio. So this is our key element. This is giving, because first 60 by 3 by 4 it was giving 80, 30 by 2 by 4 it is giving 60, then it is giving 160, 60 is minimum. So the minimum is coming with respect to second row. Earlier the minimum ratio was coming with respect to third row. Now it is second row, first column and second row. Okay. Now once we have got this 2 by 4, this 2 by 4 is nothing but half, you can say. This is giving the minimum ratio, positive ratio. So we want to formulate a new table. First one is table 0. Now it is table 1. Next is table 2. This table 2. So first what the work? We will relabel. So relabel in the first column and in the second row. So in place of minus x1, so we'll have here minus z2. In place of minus x1, we'll have here minus z2. In place of z2, we'll have here x1. Okay, that is the, so x1 becoming the entering variable and z2 is becoming the departing variable. So this x1 is our new basic variable and z2 is becoming the non-basic variables. Every time one is becoming basic variable, other is becoming non-basic variable. Only there is this much change, no other change. Other labels you make it as it is. So in place of minus x1 put minus z2, in place of z2 put x1, other label remain as it is. So with respect to that, we have here, this is the new table, minus z2, minus z3, 1, z1, x1, x2, z. Now how to fill up? How to fill up? I will make it smaller inside so that you can realize. This 2 by 4, this 2 by 4, so in the next table, it will be the reciprocal. This 2 by 4 means it is half, half is becoming 2. Okay. Now in the same row, you divide by half or divide by 2 by 4. So this is becoming second row, second element. If you are dividing by 2 by 4, this is becoming minus 1. And this 30 is becoming 60. In the same column, so 3 by 4 you are dividing, this will be minus 3 by 2. So next position there is no change. 1 by 4 divided by 2 by 4 with a minus sign, that is minus half. And minus 1 by 4 divided by 2 by 4 with a minus sign, this is half. Okay, so we have completed the P position is becoming 1 by P with the row elements, with the column elements, other elements, we have to apply PQRS rule. Now see here, this with respect to I'm talking about the right hand side value. Let us see here, 2 by 4 into 60, 2 by 4 into 60 minus 30 into 3 by 4 divided by 2 by 4. So this is becoming 15. You can verify 2 by 4 into 60. 2 by 4 into 60 minus 3 by 4 into 30 divided by 2 by 4. This is coming as 15. So second row we have completed. Third row 2 by 4 into 40 minus 2 by 4 into 40 minus 1 by 4 into 30 divided by 2 by 4. This is becoming 25. And you can see here in the position 120, 2 by 4 into 120 minus plus 1 by 4 into 30 divided by 2 by 4. This is coming as 135. You now complete all other elements using the rule PQRS method. That is P into S minus Q into R divided by P. Okay. So once you complete, what do you find here? So we find a table like this. So in this table, we have to take the conclusion. This table, we have to take the conclusion. What is the conclusion here? This is called a optimal simplex table. Optimal simplex table. So why optimal? Is there any negative element in the last row of the simplex table other than the D position? Is there any negative element? What is your answer?
There isn't.
No negative element. So it is optimal. And
Sir,
this is a solution, optimal solution you are finding. So what is the optimal solution? So in the problem itself, we are needing x1, x2 only. Now, what is your x1? X1 is becoming 60. What is your x2? X2 is becoming 25. What is your z? Z is becoming 135. What is our z1? Z1 equal to 15. Why you are calculating all these things? These are the basic variable. Z1 is a basic variable, 15. So x1 60, that is a basic variable, x2 25, and z equal to 135. Okay. So this is already I have mentioned here x1 equal to 60, x2 equal to 25, z equal to 135. This is the optimal solution. And these are the two non-basic variables z2 and z3. z2 and z3 they are 0. Basic variable z1 equal to 15. Now let us verify in the problem. We have here, this is the constants x1 plus x2 plus z1 equal to 100. What is x1? x1 equal to, you got 60 and x2 25. 25 plus 60 85. z1 15. Say total equal to 100. Then x1 60. Then x2 25. 60 plus 50 and z2 equal to 0. So we got here 110. x1 60, x2 25, 60 plus 100, 160, and z3 equal to 0. So all are fulfilled. And what is the value of the z? Z equal to x1 plus 3x2. x1 equal to 60, 3x2, 25 into 3, 75, 60 plus 75, that is 135. This is got the optimal solution. Now, the question is, so this is a optimal solution, whether we have this is the only optimal solution or any other optimal solution? The answer is no, there is no other optimal solution. Instead of this half, two halves are there. Instead of this, if one of them is 0, then we can say that yes, there may be optimal, alternate optimal solution. Alternate optimal solution. Okay, this. Is it clear?
Sir?
Yes.
Sir, in the first row, second column, it is coming plus 1 by 2 instead of minus 1 by 2, sir.
Yes.
So in the last table, this one,
Yes, sir, in the table 2. Yes, sir.
it is coming. See,
Plus 1 by
now since you have got an optimal table, whether plus or minus, so
Yes, sir. That
the
doesn't.
result will not change, but
Yes,
you
sir.
can change it. Okay, you can change. That may be a mistake also. Okay. This numerical value, there is a negative sign you are saying, in a positive sign.
Yes, sir.
Which row? Tell me again.
First row, second column.
First
Minus
row,
1
second
by 2
column.
instead of plus 1 by 2.
Okay, that is okay. 1 by 2. Okay, all right. But no other change. The right hand side value. See, in fact, in the last table, these are crucial. The value of the basic variables, value of the non-basic variable, value of the objective functions, they are crucial. So this inside table, whatever you are there in the last table, cannot be crucial, but there should not be any mistake. So if it is mistake, you correct it. Okay, this is plus half. Okay, that's all. Is it all right? Should I repeat? See, specifically, we have discussed a problem. We have discussed a problem. Only slack variables are there. Slack variables and actual variables, actual decision variables, slack variables. Surplus variables, artificial variables are not there. If surplus variable, artificial variables are there, this method is no longer applicable. I am repeating again. This is a problem. We have only slack variables. X1, X2 are the decision variables. The slack variables are there. Z1, Z2, Z3 are the slack variables. No artificial variables, no surplus variable. So directly this table is applicable directly. But if surplus variable and artificial variables are there, this table we have to modify. This table we have to modify. Now the question is, how do we modify? Now we have some answer. Here I am going to the next problem. See, this is a problem. Say maximize z equal to 2x1 plus 3x2. See, this problem you can solve graphically. We are not going to discuss this present problem graphically. We are going to discuss about the simplex method. So directly simplex method is not applicable. Why? Why it is not applicable? See, maximize z equal to 2x1 plus 3x2. Okay. subject to 2x1 plus 3x2 equal to 12, 2x1 plus x2 greater than or equal to 8, and x1, x2 are non-negative. See, I have told you, whenever there is a equality constraint, we introduce right hand side is positive, we introduce artificial variables. When there is a greater than equal type constraint, we introduce a surplus variable and a artificial variables. Okay, right? So how many artificial variables are needed in this problem? What is your answer? In first constraint, one artificial variable. In second constraint, one surplus variable, one artificial variables. So we can express in this manner: 2x1 plus 3x2 equal to 12. Now you may ask me, the first equation is already, first constraint is already an equation. Why there again you want to make it equation? No, we are going to use a basic variable. We are introducing a basic variable for each constraint, whether it is equation or inequation, hardly matter. We will introduce a basic variables. So 2x1 plus 3x2 equal to 12. Now 2x1 plus 3x2 plus z1 equal to 12. I am adding something z1. This is called an artificial variable, artificially added. We have to make in final table this artificial variables 0. If you cannot make 0, then our solution is infeasible. Okay, artificial variables, artificially added. What is the, you see in the chemistry we use some determinant, some detergent to start the reaction. Okay, so there is no purpose here, simply the z1. What we are saying, z1 is artificial variables, artificially added to help us to find the solution. If the artificial variables you cannot make 0, then the problem is infeasible, will conclude. Okay, z1 is clear. Now second inequation, 2x1 plus x2 greater than or equal to 8. So we are writing in this manner: 2x1 plus x2 minus x3. This x3 is a surplus variable, plus z2, that is artificial variable, equal to 8. Now how many artificial variables are there? How many artificial variables are there? z1 is artificial variables, I am naming. z2 another artificial variables. There are 2 artificial variables. Okay, these 2 artificial variables artificially added, their value has to be 0. Okay, now we have objective function. What is the objective function? 2x1 plus 3x2. Now we are formulating a new objective function in this manner. So my new objective function equal to z equal to 2x1 plus 3x2 minus m times z1 plus z2. What is m? M is a large positive number. M is a large positive number. Now see, if z1 and z2, they are generally non-negative. If they are becoming 0, minimum value is 0. If you make this z1, z2 0, then it is fine. In case z1, z2, we are unable to minimize, let me say their value is something like, say z1 is becoming 0.1, z2 becoming 0.2. Okay, so minus m times, m is a very large positive number. So this minus m times, say 0.1 if you are 0.1 plus 0.2 if you are adding 0.3, minus m into 0.3. That is also a very huge number, big number. So that big number should be subtracted from the objective function. Once it is subtracted, so this will not be the optimum solution. It is something else. But if you can make z1, z2 0, z1, z2 0, then it is fine. So what we are doing, we are introducing a penalty for this z1 and z2. This penalty m is a very large positive number, minus m times. So this due to this penalty, we'll try to remove these artificial variables. This is the trick we are using. So this is minus m times z1 plus z2. Okay, that's all. So in the new objective function, so this will be 2x1 plus 3x2 minus m times z1 plus z2. Okay.
Sir, you are muted, sir.
Sir, you are muted.
Minus m times z1 plus z2. What is z1? You can express z1 in terms of x1 and x2. Our z1 is becoming 12 minus 2x1 minus 3x2. This is our z1. What is z2? z2 equal to 8 minus 2x1 minus x2 plus x3. You add z1 plus z2 minus m times that. So this will be, so as a result we will have 2x1 plus 3x2 minus m times, if you are adding, that is 20 minus 4x1, 20 minus 4x1 minus 4x2, okay, 4x1 minus 4x2 plus x3. So we can express in this manner. So this is equal to x1 times 2 plus 4m, x2 times 3 plus 4m minus m times x3 minus 20 times m. We will write in this manner. Okay. And what is m? M is a very large positive number. If you are writing a code, the m value you have to just supply. Depends on, okay, let me say my m equal to 10 to the power 8. Okay, let us say. Okay, or 10 to the power 10. So certainly, depending the cost coefficient, you have to give the m value. Now, whatever we have written, we want to make table. What is the table? Now, once you have done this, we can have a table. So, how many variables in this problem? I will not complete. So, I will tell you how many variables in this problem. See this? How many variables? There are 2 variables originally. We have introduced 2 artificial variables, 4, 1 surplus variable, 5. Out of the 5 variables, how many will be the basic variable? There are 2 basic variables. Basic variables are namely Z1 and Z2, and rest 3 are the non-basic variables. So in the table you can see here, the non-basic variables are x1, x2, x3. Basic variables are Z1 and Z2. And we like to formulate a table and solve using the usual method. Okay, so and these artificial variables Z1, Z2, we have to remove from the basis. Their value has to be 0. If you cannot make them 0, then the problem is infeasible. Okay, we'll stop here. You all right? You can go through the slides. I already have given the slide to you. Okay. Okay. Thank you.
Yes, sir. Thank you.
Sir,
Thank you, sir.
Any problem?
yes, sir. One, like whenever we exchange the basic and the non-basic variables, the last row, that respective last row will always be positive, will come out positive, right?
Whenever you change the basic non-basic
Variable,
last row,
the respective last row value will always come positive at last, right?
no such things.
Because you said that we wanted the last row to be all positive at last, like at the end of our process.
No. See, I am repeating here. So this is the table. I think it will be clear from this table. So this is the table. Okay. So in this table, what we are doing? So in next table, we'll interchange the rule of basic variable, non-basic variables with respect to second column and third row. Okay. Second
Yes.
column and third row. So whenever you are, see, always the basic variables value are non-negative. Okay, 0 or positive, so non-negative, it cannot be negative. And the non-basic variable always 0. Okay, so we are interchanging the value of the basic variable, non-basic variable from first to second. Okay, then again we are interchanging. Once it is completed, we are interchanging the value of the non-basic variable and the basic variable. Okay, you can see here. So this here we cannot do anything. Why? Because the table is optimal. Once the table is optimal, we cannot do anything. So that is the final table. That is your question?
Yes, sir. Like always, there will be optimal table or not?
No, see, whenever we are solving a problem, the problem not necessarily to be optimal. We may terminate after first iteration. So sometimes we find the problem is unbounded. Okay, say unbounded problem you will terminate, you will not be able to solve unbounded. Okay, then so see, using step 1 and step 4, I told you. So what is the step 1? So step 1 say that if you are finding a optimal solution, you stop here, step 1. Then so unbounded, step 3. Using step 1 and step 3, we will terminate the process. So using this algorithm, no other. Okay. So after completing the step 3, we will come to the step 1. Either we will terminate the process using step 1 or step 3. Step 3, why? Because once the problem is step 2. If it is unbounded, you cannot go to step 2, step 3. Okay. Once it is unbounded, you stop here. That's all.
Okay, sir. Thank you.
You please solve some problem. I will give you more problems so that it will be clear. Okay. Thank you.
Thank you, sir.